Hi everybody, here's our Unit 2 Test Prep Solutions video. We talked about these three graphs in class today. Here's my vertical stretch of 2 and a shift to the right 2 units. So this shape got stretched up and shifted to the right. All right, that's what it looks like. This transformation is a reflection in x and a vertical shift of 4. So think about that thing flipping over and then shifting up 4 units, and that's where it would be. Okay, number 2. Like I said in class today, there's a problem like this on the test, but it's got easier numbers. Nevertheless, what we're trying to do is to find all this stuff: domain, range, vertex, y-intercept, and the equation written in vertex form. You do not necessarily have to use completing the square process to do this. If you figure out what the coordinates of the vertex are, you can put them into the function, into that vertex form of the equation. Just keep in mind, if you're going to do it that way, this stretch factor is whatever that number a is, okay? That would not change. So negative b over 2a is the x-coordinate of the vertex. I kind of worked that out to get 3 over 10. I plug that number back into the equation to get the y-coordinate. I come out with these, so that's how I got the 0.3 and the 0.55. So the domain for all quadratics is all real numbers, and so you can just count on that one always being true. The range, however, depends on where the vertex is. This one's got this is a positive parabola because it's a positive number there for A. It has a minimum value. That minimum value, that y-coordinate of the vertex, is where the range starts. And this one being positive, it goes up to infinity. So there's your coordinates for the vertex. Kind of got that already taken care of. The y-intercept is easy. When x equals 0, just plug that in there at 0, 0, positive 1. So there's your y-intercept. Okay, here's your true-false statements right here. A function having the same output for opposite input values, like 2 and negative 2 giving the same y value, that's an even function. That almost defines an even function. Opposite inputs giving the opposite outputs is an odd function. So check those definitions for even and odd functions. Average rate of change is not the difference between x-intercepts. No. This is the average rate of change is the slope of a line between 2 points on a curve. That's what average rate of change is. Function composition, F circle G. This is not a commutative operation. So this is also a false statement. This is only true if the F and G happen to be inverses of each other. So in general, it is not true. You'll see an example of that later on. These two statements are both true about quadratic functions. Yes, they have a minimum or a maximum. That's the y-coordinate of the vertex, and they have a domain of all real numbers. Okay, evaluating this piecewise function here, the trick on this is to make sure that your input value, whatever you are using, matches the domain for each of these different pieces of the function. So this piece, 0.5x minus 2, uses the domain negative 4 to negative 2. So that includes negative 3 and negative 2. So you'd use this rule to do that evaluation. The next input value of negative 1 is in this middle domain here, and so that just equals 0 because that's what the rule is. It equals 0. The next input value, f of 0, doesn't have a place in the domain. There is no place where 0 is included. So 0 is not even the domain, nor is positive 4. Positive 4 is not in this domain. It's just less than 4, not less than or equal to. So both of these input values have no solution, all right? And then there's the output for when x equals 1. F of 1 is 2.5. All right, let's keep going. Using function composition right here, like I said, it's not a commutative operation. Here we'll try that out. Here's 2 functions, and we're going to find g of f of x first. That means take f of x and put it into g. So x squared minus 5 goes into g. 2 times x squared minus 5 gives you 2x squared minus 9. The other way around, f of g of x means to take g of x and put it into f. So 2x plus 1 squared minus 5, all right? And that works out to 4x squared plus 4x minus 4. All right, not commutative, clearly different functions. They're both quadratic, but they're not the same. All right, let's flip it over. Look at these here, pesky word problems, all right? So the first one, we talked about this a great deal in class today. I've got a square. The diagonal of that square, all right, from opposite corners, is like, well, not like, it is the hypotenuse of a 45, 45 right triangle. So using that ratio, here, let me square up, or the Pythagorean theorem, you can work out the relationship between d and x as being d equals x times the square root of 2. Now that's important because normally the area of a square is just the side length, or x, squared. But I need to write the area function in terms of d. So here's the equation that relates d with x. I solve it for x because I'm trying to eliminate x. So I'm replacing x with d over square root of 2, and that simplifies down to this lovely little fraction right here, d squared over 2. That's the area of the square in terms of the diagonal. Now this d over root 2 equals x thing will be useful in the next problem because now we're trying to express the volume of a cube. Just going one more dimension up. A cube is x cubed, so I'm going to replace x with d over root 2. And I've got 3 different ways to write that fraction. I'm going to say they're all good. The math purists among us would prefer to see this one with a rational number in the denominator of the fraction. But they're all good. It's really kind of a matter of opinion how you prefer to write that. Okay? Just replacing x with d over square root of 2 and then kind of working out the algebra. The next problem about Mr. Green Jeans' garden, okay? He's got 350 feet of fence. He's going to make a garden with one dividing fence in the middle of it. And so I've got, it's a rectangle, so that one, and that one are all the same. X, 3x, plus the 2y sides of the garden equal 350 feet. All right. Normally, I would say the area of this function of this rectangle is x times y, but I want a function that only uses one variable. So I'm going to replace the y with something else. And that something else comes from this extra equation right here. When I solve this for y, I get 175 minus 3 halves x. Y equals that. I'm going to replace the y with that. And there's my area function. Voila. Right there, or writing it in standard form here. They're both good. You can use either one, whatever you prefer. Now, to find the area, the maximum possible area, since this is an upside down parabola, it's got a maximum value, and that maximum happens when x is negative b over 2a. That's the x coordinate of the vertex. So there's b, there's a, putting that in gives me 58 1/3. A little bit awkward number. You'll have nicer numbers on the test, but the process is the same. And so that's the x dimension of this rectangle that gives me the biggest area. And the y dimension, well, I can figure out the y dimension with this little equation right here, right? Y equals this 175 minus 3 halves x. I replace the x with 58 1/3, and I get 87 1/2. So my dimensions, the biggest possible garden I can make is 58 1/3 feet by 87 1/2 feet. Now, Mr. Blue Shoes, the neighbor, comes over and adds 150 feet of fencing to his 350 that he started with, and we're also going to have an extra dividing fence. And so our garden now has 4 x's and 2 y's to make 500 feet. All right, so this is our new equation relating the x's and the y's together. We get solving it the same way, 250 minus x, minus 2x, sorry. That's my y dimension there. So my area function then is x times y, or 250 minus 2x. There's your area functions in either form. And once again, I'm trying to find the dimensions of the largest area they can make. So I need the x coordinate of the vertex of this upside down parabola. That's 62 1/2. That's this dimension. To find the y dimension there, plug it back into this equation right here. So 250 minus 2 times 62 1/2 is 125. So there's my dimension, 62 1/2 feet by 125 feet. All right, so be ready for that one tomorrow. Finding the domain of these functions. Here's a function. It's a fraction. I can't have a denominator equals 0 in a fraction, so the only number that makes the denominator 0 for this fraction is negative 1/3. So the domain is everything except that. All x not equal to negative 1/3, or in your slightly more awkward interval notation, there's the expression for the domain there. This one is a square root of something, so that something has to be greater than or equal to 0. That's a non-linear inequality, folks. So find the factors, find those special numbers that make it equal to 0, and test values in between. That would be 4 and negative 4. All right, so there's my 2 values. When I test a number in between 4 and negative 4 on the number line, such as 0, 4 minus 0 times 4 plus 0, well, That's positive. That's 4 times 4. So that's positive. And so my domain is everything that makes it positive, which is from -4 to +4. There's your domain. Okay? And next problem about average rate of change. All right, average rate of change. It's been a while since we talked about this. Hope this doesn't hit you too hard. Average rate of change is the slope of a line between 2 points. So I need the 2 points coordinates, and so I can go y minus y over x minus x. Right? That's my slope formula, y minus y over x minus x. So there's an x, the y is -16. There's another x, the y is -15 and 3/4, 15.75. So I take y minus y over x minus x. That's my slope formula. That's what average rate of change means. And so I get this value right here, 0.125 or 1/8. That is the average rate of change for this function between these two x values. It's a rather gradual, not very steep slope. To generalize that between x and any other x, all right, it's the same process. F of x is, well, that's just x squared minus 8x. There's nothing else to change there. F of x plus h, however, that's kind of a mouthful. So x squared, that's x plus h squared, minus 8x minus 8 times x plus h. So we work all of this algebra out, and hopefully you're okay with me just jumping to this final statement for that. You might have a couple of intermediate steps there, but not many really. So there you go. That's what that looks like. So again, I'm taking y minus y over x minus x. Well, in this case, x minus x, that's x plus h minus x, that's just h. So I've got this whole big long thing right here, all right, there it is, minus x squared minus 8x. And when I subtract x squared minus 8x, I get x squared plus 8x. All right, so